All right, so today we're diving into, a paper that a listener sent us and asked this really big question. Like, how do we know if something is acting more like a quantum system or more like a classical system? Basically. It's all about figuring out where that quantum world ends and that everyday world we experience begins.
Yeah, it's a fascinating question. It's kind of this puzzle, because we all know that the universe has these two completely different sets of rules, right?
So
It's like at the super tiny scale of atoms and particles, things just get totally weird. And then we have this big macroscopic world of planets and, well, coffee mugs that behave in these very predictable ways.
Right, yeah, it's like two completely different rule books. It's like, on one hand, you've got these quantum particles that are like being in multiple places at once, teleporting through barriers. It's mind-boggling. And then on the other hand, you've got your coffee mug just sitting there on the table, stubbornly refusing to teleport anywhere.
Right, exactly. So this quantum classical transition, figuring out how and when those rules change, is a pretty big deal for physics.
Yeah.
And that's where this research paper comes in.
Yeah.
It's titled Physico-Quantum Dimension, D, a framework for quantum classical transition.
It's a mouthful, but it sounds intriguing. It was published just this month, actually, January 3rd, 2025, by Kenny Lujan Rodriguez.
Yeah.
And, get this, it claims to have this formula, a single equation, that can tell you whether any system leans quantum or classical. Think of it like a quantum litmus test. So tell me, what exactly is this Physico-Quantum dimension, and how does it work?
Well, at its core, the D formula is surprisingly simple. It's a dimensionless number,
Right.
meaning it doesn't have units like meters or seconds. It's more like a score. You calculate it by comparing two components, which represents all the wacky quantum influences.
There's difference than more familiar classical.
Classical.
Okay, so that makes sense. But like, how do you even go about measuring quantumness? What kind of factors are we even talking about here?
Well, imagine like a cosmic seesaw. On one side, you've got all the quantum weirdness represented by things like the number of particles in the system, their energy levels, how hot or cold the system is, and even how isolated it is from the rest of the universe.
So the more particles you have, the more energy they have.
Yeah.
And the hotter the system is, the more likely it is to be quantum.
Yeah, exactly. And then on the other side of the seesaw, you have the classical influences, represented by A.
Okay.
This includes things like the density of the particles, how often they bump into each other or their environment, the total mass of the system, and something called coherence.
Okay. Coherence. Now remind me, what was that again?
So coherence is basically a measure of how in sync things are. So think of like a laser beam, where all the photons are marching in perfect step.
Okay.
That's a highly coherent system. And generally speaking, the higher the coherence, the stronger the quantum behavior.
Okay. So the D formula is basically like weighing all these different factors, seeing which side of the seesaw tips down, quantum or classical.
Precise. It's taking into account this intricate dance between quantum weirdness and classical solidity, weighing all these different factors to determine which side wins out.
So it's not just some theoretical equation just floating out there in the abstract. They actually put this formula to work.
Oh, absolutely.
Okay.
The paper goes through several examples of how this works in practice. For instance, they calculate D for systems that are definitely quantum, like a single isolated particle.
Yeah.
And guess what? They get strongly negative D values, which is exactly what you'd expect for something that's deep in quantum territory.
And I'm guessing for something decidedly not quantum, like, say, a planet, they get large positive D value.
You got it.
Okay.
So the formula seems to check out at both ends of the spectrum, the very quantum and the very classical. But here's where it gets really interesting.
Hit me with it. What's so interesting about the D formula?
Well, they also calculate D for systems that are somewhere in between, not purely quantum or classical. Think superfluid helium, which can flow without any resistance, or certain kinds of quantum dots, which are these tiny semiconductor crystals with unique electronic properties.
You mentioned superfluid helium. I remember seeing those videos in science class. You know, the liquid helium creeping up the sides of the container. What makes it so special? And how does this D formula help us understand its bizarre behavior?
Well, superfluid helium is a fascinating example of a system that bridges that gap between the quantum and classical worlds. It exhibits quantum behavior, like superfluidity, on a macroscopic scale, which is pretty unusual. And so the D formula can help us understand why. Superfluid helium behaves this way. It allows us to see how the interplay of different factors, like the number of helium atoms,
Right.
their energy levels, and their coherence, contribute to its unique properties.
Okay, so those in-between systems, the ones that aren't purely quantum or classical, that's where the D formula could really shine.
Exactly. It
Yeah.
could help us understand and even predict
Yeah.
when we might see these weird quantum effects pop up in bigger, more complex systems.
That's incredible. So, what does all of this mean for someone who isn't a physicist? Why should we care about this D value?
Yeah.
What are the implications here?
Well, think about it this way. If we can figure out this fuzzy boundary between the quantum and the classical, we could unlock incredible new technologies.
Okay.
Imagine designing materials or devices where you could actually dial up or down. The quantumness.
Wait, really? Like we could actually control how quantum something is? That sounds straight out of science fiction.
It might sound like it, but that's the potential here, and the implications are huge.
Yeah.
We could see revolutions in computing, sensing, communications, you name it.
Wow, so this isn't just about understanding the universe, it's about potentially controlling it at a fundamental level. But hold on, if this D formula is so revolutionary, why haven't we heard about it before? Are there any physicists who are like skeptical of these findings?
Well, it's important to remember that this is just one paper,
Right.
and the scientific community needs time to digest it, test it, challenge it. There's a lot more research that needs to be done before we can definitively say whether the D formula is the AE answer to the quantum classical question. But it's certainly generating a lot of excitement and discussion.
That makes sense. Got to keep those scientific skepticism hats on.
Okay.
But still, the possibilities are pretty mind-blowing.
Absolutely. And the paper doesn't just stop at theory. It also suggests ways we could actually test the D formula in the real world.
Oh, tell me more about these. Proposed experiments. Are we talking about
Yeah.
recreating the Big Bang in a lab?
Nothing quite that dramatic, but they do suggest some pretty intriguing experiments. For instance, we could carefully measure coherence in systems like Bose-Einstein condensates, BECs for short,
Mhm.
which are those super-cooled clouds of atoms that act like one giant quantum wave.
Okay.
Or you could look for subtle gravitational effects from dense objects in space, like neutron stars, or even black holes.
Whoa, now we're really going to the extremes. Black holes, neutron stars. It sounds like we're about to take a wild ride through the cosmos. But before we get too carried away, let's take a step back and just make sure we're all on the same page. We've thrown a lot of information at our listeners.
Yeah, good point.
So just to recap, what are the key takeaways so far? What do we really need to understand about this Physico-Quantum dimension?
I think the most important thing to grasp is that this D value gives us a potential way to quantify the boundary between the quantum and classical worlds.
Okay.
It's like having a ruler. For measuring quantumness, and the factors that go into calculating D are incredibly diverse. From the number of particles and their energy levels to their coherence. It's a remarkably holistic approach.
So it's not just some
Arbitrary.
arbitrary number. It's deeply rooted in the fundamental properties of a system.
That's exactly right.
And that means we could potentially predict how a system will behave, whether it will lean towards the weirdness of the quantum world or the familiarity
of the classical world.
That's exactly right. This is incredible
Yeah, I
what we're
agree.
talking about.
The potential to design materials that can switch between quantum and classical behavior on demand, to simulate the conditions of the early universe, to understand the very fabric of reality itself. And it all boils down to this. One, single equation.
It's pretty remarkable, isn't it?
It really is.
Yeah.
But we've only just scratched the surface of this paper, haven't we?
Yeah.
There's so much more to explore, like the specific predictions this D formula makes and how it connects to other theories of physics.
Absolutely. There's a lot more to unpack.
All right, then. I think we've given our listeners plenty to chew on for now. When we come back, we'll delve even deeper into the Physico-Quantum dimension and its potential to reshape our understanding of reality itself. Stay tuned.
Welcome back to our deep dive into the Physico-Quantum dimension. Before the break, we were talking about how we might actually be able to test this D formula, to see if it holds up in the real world.
Right, because a theory is only as good as its experimental evidence.
Exactly.
Yes.
So let's talk about those proposed experiments. You mentioned using things like Bose-Einstein condensates, BECs. You know those supercooled clouds of atoms that act like one giant quantum wave.
Yes. BECs are a great example of systems where we can precisely control and measure quantum phenomena.
Okay.
We can tweak things like the number of atoms, their energy levels, and even their interactions with each other to see how those changes affect the system's D value.
So we're essentially playing with the quantum knobs, seeing how those adjustments shift the balance between quantum and classical behavior.
Precisely. And by comparing the experimental results with the theoretical predictions of the D formula, we can start to validate its accuracy and predictive power.
Okay. So we've got these supercooled atoms. On one end of the spectrum, what about systems that are more on the classical side? How do we test the D formula there?
Well, for very classical systems, the paper suggests looking at some of the most extreme objects in the universe.
Yeah.
Neutron stars. And black holes.
Black holes. That's taking this deep dive to a whole new level. But seriously, how would we even measure the D value of something as massive and mysterious as a black hole?
It's a challenge, no doubt. But we might be able to use a phenomenon called gravitational lensing.
Okay.
That's where the gravity of a massive object, like a black hole, bends the path of light that passes by it.
Okay. So it's like looking at a distorted image through a curved lens.
Exactly.
Right.
And the amount of distortion we see can tell us about the strength of the object's gravitational field, which, according to the D formula, should be related to its D value.
So by studying how light bends around a black hole, we could indirectly measure how classical it is.
That's the idea.
Okay.
And then, of course, there's that whole range of systems that fall somewhere in between the quantum and classical extremes. You mentioned superfluid helium earlier. That's a prime example of a system that's not quite quantum, not quite classical.
Yeah.
And the D formula could be really useful in understanding those in-betweeners.
So it's not just a binary, quantum or classical. There's a whole spectrum, a gradient. And the D formula helps us navigate that.
Right. It's not just about categorizing systems as either quantum or classical. It's about understanding that there's a continuum between those two extremes.
Okay.
And the D formula gives us a tool to explore that continuum, to see how subtle changes in a system's properties can tip the scales towards one regime or the other.
All right. I'm really starting to see how powerful this D formula could be. But it also makes me wonder how it fits in with everything else we know about physics. Does it clash with any existing theories like quantum mechanics or general relativity?
That's a great question, and one that the paper addresses directly.
Right.
The good news is that the D formula seems to be compatible with our current understanding of physics.
So it's not like it's throwing out all the physics textbooks and starting from scratch.
No, not at all.
Right.
Think of it more like an extension, a refinement. It takes the principles we already understand and applies them in a new, more comprehensive way.
So
it's not replacing our current understanding of physics. It's building on it.
exactly.
Well,
For instance, in situations where quantum mechanics already reigns supreme, the D formula simply confirms what we already know. It's like a double check, a validation of existing theories.
okay.
And similarly, in situations where classical physics is clearly dominant, the D formula agrees.
With those predictions as well.
So it's consistent across the board. But the real power comes from its ability to tackle those in-between situations, the ones where it's not immediately clear whether quantum or classical rules will prevail.
Precisely.
Okay.
And that's where things get really exciting, because the D formula doesn't just tell us which regime a system falls into, it also provides insights into the transition itself.
It gives us a way to see how the sausage is made, so to speak.
Exactly. It helps us understand the mechanisms behind this. Quantum classical interplay.
Okay. Let's go back to something you mentioned earlier, the connection to the early universe. We briefly touched upon this in the first part, but I'd love to hear more about how this D formula could help us understand what happened in the first moments after the Big Bang.
Well, imagine the early universe, just fractions of a second. After the Big Bang,
Okay.
it's incredibly hot, dense, chaotic. It's a cosmic soup of energy and particles, all crammed together in a tiny space.
It sounds like my kitchen. After I try a new recipe. Controlled chaos.
Yeah, maybe a little less messy, but you get the idea.
Yeah.
Under those extreme conditions, it's believed that quantum effects would have played a significant role in shaping the universe as we know it.
So the laws of physics, as we know them, might have been completely different back then.
Potentially, yes. And that's where the D formula could be incredibly valuable. It could help us model those early conditions, see how the transition from a quantum-dominated universe to a classical one might have unfolded
So we could essentially rewind the clock and see how the universe evolved from its quantum infancy to the more classical universe we see today.
That's the hope, of course. It's an incredibly complex problem,
Right.
and there are still many unknowns.
Yeah.
But the D formula gives us a new tool, a new lens, through which to view those early moments.
It's amazing to think that we might be able to use this formula to unravel some of the biggest mysteries
Yeah.
of the universe. It's like having a Rosetta Stone for the Big Bang.
It's certainly a powerful concept, and the fact that it's rooted in fundamental physics, rather than relying on ad hoc adjustments or arbitrary parameters, makes it all the more complex.
It's not just some mathematical trickery. It's a reflection of the universe, its underlying principles, okay?
And that's why this research is so exciting. It has the potential to fundamentally change our understanding of how the universe works, from the smallest scales to the largest.
Okay. I think my brain is officially full. We've covered a lot of ground today. From super-cooled atoms to black holes to the origins of the universe. Any final thoughts before we wrap up this part of our deep dive? Welcome back to the deep dive. We've been on quite a journey with this mind-bending concept, the Physico-Quantum dimension, or D for short.
Yeah, we've seen how it could potentially change the way we look at everything from tiny quantum systems to the vastness of the universe.
Right, and we've talked about the possibility of testing this D formula in the real world.
Using
Experiments with things like Bose-Einstein condensates. And
even black holes.
Right.
Yeah.
But now I want to kind of step back and think about the bigger picture. What could the D formula mean for the future of physics? What are the long-term implications?
Okay, let's get philosophical. Hit me with those big picture thoughts.
Well, if the D formula holds up under further scrutiny, it could fundamentally change how we view the universe. Right now we tend to think of the quantum world and the classical world as separate domains, which makes sense. That's how we experience reality, right? Like my coffee mug stays put on the table. It doesn't suddenly decide to exist in multiple places at once.
Exactly.
Yeah.
But the D formula suggests that the boundary between these two worlds isn't so clear-cut. It's not a case of either, but rather a spectrum, a continuous transition between the two.
So there's not a sharp dividing line. It's more like
a gradient,
a smooth blending of quantum and classical.
Precisely. And that could have profound implications for how we approach physics. It suggests that there might not be two sets of rules, one for the quantum world and one for the classical world, but rather a single unified set of rules that govern everything.
Okay, so instead of two separate physics textbooks, there's really just one master rule book. And the D formula might help us understand how to read it.
That's the idea.
Okay.
It could be the key to unlocking the secrets of this unified rulebook, to understanding how the same underlying principles give rise to both the bizarre behavior of quantum particles and the familial behavior of everyday objects.
That would be huge, a complete paradigm shift in physics. It's like discovering the missing link between two seemingly separate species.
It really is.
Yeah.
It would mean that the universe is
Yeah.
even more interconnected and holistic than we currently imagine. Everything would be linked, woven together by this single set of rules.
And what about the practical implications? Like if we could actually control this D value, what kind of technologies could we develop? What would a D value technology even look like?
The possibilities are mind-boggling.
Yeah.
Imagine being able to design materials with specific D values tailored for specific applications. We could essentially engineer materials that exhibit the best of both worlds, the stability and predictability of classical objects with the unique properties of quantum systems.
So we could create materials that are super strong and durable, but also have these weird quantum capabilities. That would be revolutionary for fields like engineering and material science.
Absolutely.
Yeah.
Think about quantum computers. They rely on these delicate quantum states that are easily disrupted by the environment. But what if we could create materials that shield these quantum states from interference, effectively dialing up their D value to make them more robust and reliable?
That would be a huge breakthrough for quantum computing. That would make them much more practical and accessible.
Exactly. Or think about energy storage. Imagine batteries that exploit quantum effects to store and release energy with unprecedented efficiency, or solar panels that capture and convert sunlight with near-perfect efficiency. The D formula could open up entirely new avenues for sustainable energy technologies.
Sounds like we're talking about a future where the line between science fiction And reality
Yeah.
becomes incredibly blurred.
It might sound far-fetched, but remember,
Yeah.
just a few decades ago, things like lasers and smartphones were considered science fiction. Like,
Bigger?
technology has a way of catching up to imagination, especially when we have a deeper understanding of the fundamental principles at play.
That's true. The history of science is full of examples where seemingly abstract theories eventually lead to groundbreaking technologies. Who knows what incredible inventions await us once we unlock the secrets of the D formula.
It's an exciting time to be alive, isn't it?
It really is, but this whole concept is incredibly exciting, but also a bit daunting. It challenges our basic understanding of how the universe works. So what's the one key message you want our listeners to take away from this deep dive into the physico-quantum dimension?
I'd say this. The universe is full of mysteries, full of things that challenge our intuition and our current understanding. But that's what makes science so fascinating. It's a constant process of discovery, of pushing the boundaries of knowledge. And the D formula is a perfect example of that.
That's a reminder that we're still just scratching the surface
Yeah.
of what we know about the universe, and there's always more to learn.
Exactly.
Yeah.
Even our most fundamental assumptions about reality can be overturned by new discoveries. So keep questioning, keep exploring, and keep an open mind.
Well said. And on that note, I want to thank our listeners for joining us on this deep dive into the mind-bending world of the physico-quantum dimension.
It's been a pleasure exploring these concepts with you.
And if you're as intrigued by this research as we are, be sure to check out the full paper by Kenny Lou Jean Rodriguez. We'll include a link in the show notes. Until next time, keep diving deep.
And remember, the universe is a fascinating place, full of wonder and mystery. Never stop exploring it.